Let us look at proposition number 18 and the last proposition of book 12 of Euclid's Elements. The proposition says spheres are to one another in triplicate ratio of their diameters. So let's see how we can prove this. Let ABC and DEF be two spheres and let BC and EF be their diameters. What the proposition is saying is that sphere ABC is to sphere DEF as the triplicate ratio of BC is to EF. Let ABC is to sphere GHK, which is lesser than the sphere DEF, equal to BC cube is to EF cube. Now, why are we doing this? Because to prove this statement, we are going to assume the opposite, that it is not equal to the triplicate ratio of BC is to EF. So, which means there must be some other sphere which is satisfying this proportionality. So, here that sphere can be less than DEF or it could be greater than sphere DEF. So, first case we are taking up a sphere which is less than sphere DEF. Now, let sphere DEF be about the same center with sphere GHK. So, basically, we are having this sphere GHK with the same center as the sphere DEF. So, let's draw that sphere and let's say its diameter is HK. So, HKG is the sphere which is less than the sphere DEF, which satisfies this proportionality. Now, inscribe in the greater sphere DEF a polyhedral solid which does not touch the lesser sphere GHK. In the previous proposition itself, we saw we are not going to actually do that, but you have to keep in mind that we have drawn a polyhedral solid which does not touch the inner sphere GHK. And again, inscribe in the sphere ABC a polyhedral solid similar to the polyhedral solid in the sphere DEF. We know that polyhedral solid in ABC is to polyhedral solid in DEF as the triplicate ratio of their diameters. And here we started off by saying that sphere ABC is to sphere GHK is equal to the triplicate ratio of BC is to EF. So if you look at these two, then the right hand sides are equal. That means the left hand sides must also be equal. So that means a sphere ABC is to sphere GHK as polyhedral solid in ABC is to polyhedral solid in DEF. Sphere ABC is to polyhedral solid in the sphere ABC is equal to sphere GHK is to polyhedral solid in DEF. Basically, we are looking at it alternately. So, here in this proportionality, we know that sphere ABC is greater than the polyhedral solid in sphere ABC because it is going to be inscribed. So, sphere will be greater than the solid inscribed, which implies right hand side of this proportionality also satisfies that property. That is, sphere GHK is greater than polyhedral solid in the sphere DEF. But polyhedral solid in DEF is enclosed in the sphere DEF and does not touch sphere GHK. So, which means sphere GHK cannot be greater than the polyhedral solid in sphere DEF. So, we have arrived at a contradiction. So, that means our assumption that some other sphere GHK which is less than sphere DEF satisfies this proportionality is wrong. Okay, now let's look at what happens if it is greater. So let sphere ABC is to sphere LMN, which is greater than sphere DEF, is equal to the triplicate ratio of BC is to EF. So let's bring in that sphere. Inversely, we can write this proportionality as sphere LMN is to sphere ABC as the triplicate ratio of EF is to BC. And since sphere LMN is greater than sphere DEF, therefore sphere DEF is to some sphere less than sphere ABC is equal to EF cube is to BC cube. This brings us back to the first case, which we have already proved that it is not possible. So since it was proved impossible, we can say sphere ABC is to any sphere less than or greater than sphere DEF is not equal to the triplicate ratio of BC is to EF. So that means sphere ABC is to sphere DEF is equal to the triplicate ratio of BC is to EF, which is what we had to prove. So that is proposition number 18 of book 12 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.